So again, we're looking at in 8-4. We're going to start talking about vectors. Now, some of you guys that have had physics may feel very comfortable with this, but some of you guys probably have never seen this stuff before. So we're going to try to go through it as slowly as we can. Okay. Can you guys see that all right? Or is that, can you guys see that all right? Is that clear or not clear?
It's good.
Okay. So again, we're talking about vectors in this thing, and at first, the first beginning of this, you're going to be like, how in the world does this connect to what we've been doing? After we get to about the fifth example, you'll see that there's going to be a direct crossover from what we're doing today to what we've been doing in the last few sections. But it's going to be kind of a circle to get there. So we're talking about a vector. A vector has both length and direction. Length and direction. Those are kind of the two. We got to make sure we're careful about that. We normally write a vector as AB. So it's got AB with an arrow pointing one direction. In geometry, we refer to that as a ray. So that's going from point A towards point B. Okay, from A towards B. Okay. And oftentimes we don't write this as 2 points, we just write it as one. So that in this case, you could write it as U, again, with that arrow pointing one direction. Okay? Now you can write that down however you want, or if you want to circle it in your book or whatever. But again, vectors, one direction, it's got length and direction. Okay? So we'll start super easy. Super easy. So in this case, I've got this point -1, 2, which is P, and I'm going to take a vector that's going to go towards Q. So first off, I can just draw the vector, and that's going to be something simple as drawing. You're connecting the dots from point to point. This is the point -1, 2, and this is the point 3, 3, and we draw that direction on our vector. Okay. And we can write that as vector PQ. I'm not going to think that any of you guys are going to have issue with that. Okay? Real quickly, if you want to take a look, this is your example. You can put this in your notes real quick. Draw a vector that travels from the origin to 3, 5. The origin is going to be 0, 0. 3, 5 is going to be somewhere up here. That's going to be the point 3, 5. A vector is going to look something like that. Okay. Now, again, you normally wouldn't put the dots there, but I'm just putting a dot to show that point. Now, we said a vector has length and direction. Okay. This has a starting point and an end point, and I could find that length, and we're going to in just a little bit. But for right now, we're just drawing the vector. So we've done that. We've done that sufficiently. Okay. Any thoughts as to how I could find the actual length of that vector, which we're going to do in a minute, but right now we're just going to, let's jump to Shelby Patton. How could I find the length of that vector?
Would it have something to do with making a triangle?
Exactly. I could make this triangle just like this. What's my X coordinate would be 3. My Y coordinate would be 5, right? So the length of this vector would simply just be a result of Pythagorean theorem. Okay. Now this question just asks you to draw it, so you didn't actually have to find the length, but we are going to do that in a minute. Okay. Questions there? So far, so good. Now, vectors we can treat many different ways, but we can simply add vectors. We can add vectors very simply. And if you think about this geometrically, and again, this is in your book, if I have vector U is going this direction, and I have vector V that is going this direction. So U and V. If I add those together from starting point to the end of U, and then from starting point to the end of V, essentially what I have is the sum is going to be from starting point of view to the ending point of v. Okay, so what I have here, this u plus v right here, is going to be both directions put together. Okay, again, starting point of view to the end of u, starting point of v to the end of v is going to be the starting point of u to the ending point of v. Okay, and that property is here. The sum of u plus v is a vector from the beginning of u to the end of v. Okay, and that's just geometrically that we can show that with a picture. Okay, as you look down here, same idea. If u is a vector that's going up and v is a vector going kind of up to the right, well, the starting point of u would be down here. So u is going to go up, so the end of u is right here. V is this direction, so I'm going to go here. And then u plus v is going to be from the starting of u to the end of v, something like that. Okay, again, you're really just plotting points and connecting the dots. So there's not a whole lot of extra here. Now, one thing that's interesting in geometry here is oftentimes when you add two things together, you get a bigger value. But if you think about u plus v, is u plus v going to be larger than the distance of u and the distance of v, or less than the distance of u and the distance of v? Let's go to Gabriel. Gabriel, you with us? Okay, let's go to Elliot. Is this distance right here, u plus v, is it going to be larger or longer or shorter than the distance of u and the distance of v put together? What do you think? Come on now, Elliot. Addison, what do you think?
So, of you, would it not be the same? Am I seeing it wrong?
Let's say that the distance of u, I'm just making up an example, was 3, and the distance of v was 2. Okay? Would u plus b, v, this vector here, would it be longer than 5 or would it be shorter than 5?
Oh, it would be shorter.
Yeah, it would definitely be shorter than 5. This is a unique property to vectors that doesn't really apply anywhere else. If anywhere else, if you add 2 plus 3, you're going to get 5. But in this case, when I add these two vectors, the result, that sum of the vectors, is actually going to be a smaller value because we've got that direction in play. Okay. Now that's not going to come into play for right now, but it is a very interesting point. So you need to be very careful when you're adding these vectors. Okay. Okay. Now we're going to talk about scaling or scalar multiplication as you jump down through here. Okay. If I were looking at 3u, so I'm taking 3 times the vector u. Essentially, we know just from algebra that that's u plus u plus u. Okay. So really, u is one direction. That's going to be going a direction, and I'm going to go that same direction, and then I'm going to go that same direction again. So if I were thinking about this, let's say that this is u, and I want to multiply that by 3. Well, I'm going to go that same direction, that same length, that's going to be u. And that same direction and the same length, that's going to be u. So notice that I'm going the same direction at roughly the same length. I know my picture is not perfect. U plus u plus u. This entire vector becomes 3u. Okay. Now, we also want to talk about the negative. If I want to talk about negative u, right, that's simply going back the other direction, keeping in mind that the u is the same length. That's going to be negative u, going the same direction. Okay, just really like with our negative angles, we're going back the other direction. if you had pi and negative pi, when we talked about, when we were talking on our unit circle, pi is one direction, negative pi is another direction. Same idea, same idea, okay? Now, here's a little property right here that I do think it's very important, okay? If I take u plus negative u, if I go u this direction, that's u, and then I do a negative u, and I'm going to go back the same direction, okay? Where am I going to end up? Jenna?
Origin, like 0.
Yeah, I'm going to start right back here. So u plus negative u is going to end up right back at the origin, which is 0, which is going to be right back at the origin, okay? Sorry that that's a little blurry. I don't really like that. You gotta love these document cameras. Okay. Questions there? So let's jump to the next section. So we can scale a vector simply just by multiplication. So there's nothing to that. We kind of already stated that. Anytime we put a number, it's called a scalar. So 3 times u works pretty simply. We kind of already illustrated this. So 3u, if I've got 3 sections of u, that's the same thing as 3u. Negative u is going to be the opposite direction, okay? Negative 2u, again, the negative is going to reverse the direction, multiply by 2. Again, we're moving back that other direction, okay? Okay. Now, this gets a little bit tricky, and I'm going to cover this up for just a second, okay? Because I don't want you to see this right away. If u goes vertically and v goes kind of up to the right, if I think about this as u and negative v, that's going to be going up, and normally v would go up and to the right. But instead, I've turned that negative, so now that's going to go down and to the left. So if u is going up, instead of going upright with a positive v, I'm going down left with a negative v. So u minus v is actually going to be this other direction, okay? And that's where, and we're going to end up there to the left, okay? I hope that was clear. Okay, so let's talk for just a second. Let's say that I had v plus u. Directionally, somebody want to show, kind of explain, Adam, where would that be if I had u plus v? I'm assuming that I'm starting at the origin. Where would u or v plus uv, using this analogy?
Over to the right and up.
So it's going to look something like this. And then that's going to be the v part. Where's the u part going to go?
From the x-axis up.
Well, it's going to, well, again, I've started with v. So v is this movement here. And then u is going to go which direction?
Up.
So it's going to go from here straight up. So u plus v is actually going to be from the origin up to that spot right there. Okay, this would be u plus v. Okay, follow that? Let me jump to Shelby Patton. What if I had v minus u? V minus u. Where would that go? I'm going to start out at this point right here. Let's not put an origin there. Where would v minus u go?
You start from that point and go like to the right, then up a little bit.
Okay, that's my v. Where's minus u going to go?
And then you just go down.
I'm going to go down, something like this. Now, I'd have to be really careful about making sure my links are exactly right, but I'm not going to go crazy. I'm not going to be crazy picky. So V minus U is actually going to be this kind of direction, something like that. Okay.
Can you move your paper over?
Oh, I'm sorry. Sorry. So V went up this direction. Okay. That's just same as here. And then U would go up. So negative U is going to go down. So the endpoint is going to be somewhere down here. Again, I'm going to be careful. I don't know exactly what that length is. I didn't measure it out. So V minus U is going to go something like that. Okay. Now, the only thing I'm going to say that I don't want to say I'm being picky on, but I'll be a little picky on is I want you to make sure that you label the right vector. So I would draw these out in the direct, just like I did right here. This is V, this is minus U, but this vector right here is V minus U. Okay. A lot of times we might give that another name. We might say that W equals V minus U, right? We could write something like that just so that I can give that a name W or something like that. And you'll see that in some of the examples we go on forward. Okay? Questions there? Okay. Now we get to part that's a little bit tougher. So we're kind of getting back to the idea of our unit circle. Okay. So a vector U can be described by its magnitude. Magnitude is a very important word. Magnitude and length represent the same thing. Okay, magnitude and length represent the same thing when it pertains to vectors. Okay, and that's represented with the absolute value sign. Okay, now be careful. This isn't really the absolute value, right? But it's just using the same notation. This is the magnitude of vector U. Okay, we also want to be able to find its angle. Okay, and this is where all of our polar information comes from, all of our unit circle stuff. This is where we're going to tie all this together. Okay, if a vector has length 1, it is called a unit vector. So essentially, any vector that lies on the outside of our unit circle. Remember, everything on a unit circle has a length of 1. Okay, remember our unit circle. That's going to be 1 0, 0 1, negative 1 0, and 0 negative 1. Right? You have this kind of unit circle. It looks something like this. Any vector that has that radius there, okay, a radius of 1, okay, is going to be called a unit vector. Okay. Now we know a lot of information about this unit circle from this semester. Okay, so we're going to be able to use that information to tie that in here. Okay. Now, one additional way to write vectors is what's called the component form. And this is probably the more common form when we're dealing with polars and dealing with magnitudes, is we want to be able to write a vector in terms of its x coordinate and its y coordinate, because that's probably more useful to us. Having a direction isn't always super valuable, but we want to be able to, if we can find its coordinates, we can tackle it that way. Now, notice that there's these symbols here. In upper level mathematics, that's called the order of the vector, or the order of a specific term or series or sequence or whatever. But notice that that's kind of a triangle bracket there. And that represents x units horizontally and y units vertically. That's really no different than anything else you've ever done in algebra 1, algebra 2, okay? So the vector U is a direction that kind of up and to the right in this particular example. So we formed a theta, right? Also, we talked about reference angles from previous chapters. Okay, so we have an x component and we have a y component. Okay, we also know that this right here is also our r value. So all of our formulas kind of crop up. Okay, the cosine of theta is going to be x over r. The sine of theta is going to be y over r. If I solve for r is going to be y sine of theta. All those things from earlier sections are going to show up because now I've formed these nice, pretty right triangles. Okay. Okay. Sorry if that made you sick. Okay. So we have two vectors. We want to write this as a combination. So we have vector I, vector j. And we want to, so I points to the right. That's a unit vector, so we know it has length 1. Right? So a unit vector that points, I want to just kind of draw this up here. If it says it points to the right, and it's got a unit, it's a unit vector, it's got a length 1. So that's going to be 1, 0. Okay. J points up, so that's going to point up here. That's going to be 0, 1. Again, 2 points on our unit circle. So I points this direction and J points that direction. So in other words, I is 1, 0. Notice that it's got the marks on there. Okay, or the triangle brackets on there. And J has this. So in this notation, the vector U, 3, 4 could be written as 3 of the i's. Notice that I can multiply this one by 3. 3 times 1 is 3. 3 times 0 is 0. And then 4j, it's going to be 4 times 0 is 0, and then 4 times 1 is 4. This is just using that scalar multiplication. So I could write this as 3i minus 4j. Okay? Let me say that again. If I multiply this times 3 and multiply this one times 4, this would be 3, 0. This would be, this times negative 4. That's going to be 0, negative 4. When I combine those two things, I get 3, negative 4. I'm so sorry you couldn't see that, could you? Oh, yeah, you could. Okay, sorry. Okay. So, and we often use this, especially when we're talking about complex numbers, and we're not going to get into that far, but they use this a lot when we're talking about the complex plane, where we've written things as a plus bi. Again, if you guys study further mathematics, you may get into some of that kind of stuff where you've got to multiply vectors in complex form. And there's several uses for that in physics, especially when we get into 3 dimensions where you have an I, J, and a K. Again, we're not there, and we're not going there yet, but you guys might when you get older. Okay. So let's get into some actual computation. We've kind of given you all the rules. We've given you all the scenarios. But let's get into some actual computations. Okay. So we've got a component vector of length 7 at an angle of 135 degrees. So I always recommend drawing that out. Always recommend drawing that out. I'm going to cover this up. I wish I could cover it up better than what I did. Let me see if I can find it. I'll be right. So first of all, where's 135 degrees? Let me jump to Trevor. Where's 135 degrees? Trevor, you with us?
Second quadrant. Sorry about that.
Second quadrant, that's going to be this direction, right? That's 135 degrees. And I know that I have a length of 7. Okay. So the question is what kind of triangle is that? Let me jump to Elliot. What kind of triangle is that? Anybody? Come on now.
5-degree triangle.
That's 45, 45, 90, right? So remember that you've got the square root of 2. If you pull up your unit circle, you're going to see that this point right here, that's going to be the square root of 2 over 2. This is going to be negative square root of 2 over 2, right? You can see that that's going to be those cosine values of this. Now, conversion formulas, again, this is from our second lesson back here. I want to keep these handy. Keep these handy, okay? So we can find in this case that x equals r cosine of theta. So r, that's going to be cosine of 135. You wouldn't necessarily have to write this down. I know that the cosine of 135 is going to be what? Elliot. Elliot, you with us? Maybe not. Addison, well, let's go first. What's R going to be, Addison?
R, isn't that 7?
That's going to be 7. And then the cosine of 135. Again, use your unit circle or your calculator. Again, be careful with your calculator because it's going to give you a decimal. I'd rather not make it decimals. Adam, what's going to be the cosine of 135? I know you've got it right here.
Is it 0.7 or negative 0.7?
Again, we're going to use your chart. Don't make it decimals. That's going to be negative square root of 2 over 2, which, yes, it is correct. That is going to be negative 0.707. So the x is going to end up being negative 7 radical 2 over 2, which is what you have right here. And conversely, the y is going to be the same idea. R is still 7, but the y is going to be the sine of theta. Sine of theta is going to be this value right here. Okay. Again, feel free to use your unit circle. If you don't have a unit circle, we can look back in the chapters before. There is one back in the earlier in your book. I'd have to find out exactly what page it is on. I can list that in the assignment. Okay. So this vector can be written in component form as this. Again, this represents my x. This represents my y. Okay. Questions there? Now, dumb question. Is this vector a unit vector? Is this vector a unit vector? Gabriel, what do you think?
Yes.
You think that it is a unit vector or it is not? You said yes?
I think that it is a unit vector.
Okay. I'm going to argue with you as to why it's not. What is the length of a unit vector? What does the length have to be of a unit vector? I'm not actually arguing with you. I'm sorry. Remember, unit vectors by definition have to have a length of what? Shelby Patton.
1.
1. So what's the length of this particular vector? Shelby Casey. I can't hear you. I'm sorry. If you said something, I'm sorry.
7.
Yeah, in this case, we know that the radius of this thing, the length of this vector is 7. So it's definitely not a unit vector. Okay, it is a vector. And notice they didn't say that. Unit vectors are only going to have length 1. Okay. Okie dokie. Let's jump to one more type of example. I am going to save the word problems. We're going to do that on Friday. So we're just going to kind of do some of the computation stuff today, and then we're going to do the word problems on Friday. Okay. Let's jump to example 6. Again, if there's any chance you can cover up at, I know it's kind of silly. We want to find the magnitude. Again, magnitude represents the same thing as length of this vector u. Okay. So I really just need to graph that out. So 3, -2, that's going to be 3, -2. It's going to be somewhere down in here. So we're talking about this vector right there, where this is 3 and this is -2. So I've essentially made a triangle. Now I simply need to find the length or the magnitude. Again, this is length. How am I going to do that? Well, we kind of touched on this. Jenna, what do you think?
You're going to input those as your x and y values. Oh, you already have that, right? And you're going to solve for it with Pythagorean theorem.
Pythagorean theorem. So I've got 3 squared plus -2 squared equals r squared. So it's going to be 9 plus 4 equals r squared. So 13 equals r squared, square root, r equals square root of 13. So the length of this vector is going to be, this is going to be the square root of 13. It's really just a Pythagorean theorem problem. Now, again, remember that a vector has length and distance, but in this case, it asks for the angle as well. So if I know this angle, how would I find this angle right here? How would I find that angle? Well, I could really use any of the trig functions. Now that I have my r, I have x, I have y, I have r, I could use any of them. The book says use tangent. You could use sine, you could use cosine, you could use any of them. It really wouldn't matter. So in this case, the tangent of theta is going to equal what? I know that you guys can cheat with your book. What would that look like in this case? Let's go to, who have I not heard from? We'll jump back to Elliot. Can you hear me? Are you with us? Come on now, Mr. Brown. Okay, Addison, what you got? What do you think?
It would be -2/3.
-2/3. If I do the inverse tangent, sorry, of -2/3, I can find my angle. Now be careful when you plug this in to your calculator, you're going to get theta equals -33.69. Now remember that negative angles go direct backwards. How would I find the positive version of this angle? Gabriel, how would I find the positive version of that one? Okay, let's jump to Jenna. How would I find, if the negative angle is -33.69, how would I find the positive version of that angle?
One of those.
Say that again.
I said 360 minus the tangent that we got.
Yeah, so I could either add 360 to this or take 360 minus this number, and you're going to get 326.31. And again, those are in degrees. Okay, either one of these answers would be appropriate. Okay. Questions there? Okay. Again, I'm going to do one more, and then again, I told you I'm going to save the word problems for later. Let's jump to this last little piece. That's adding, subtracting. If you have vectors in component form, again, you can add, if I have two vectors, where again, notice that this is in component form. Okay. To add them, I simply am going to add the x's and add the y's. So it would be u1 plus v1, u2 plus v2. Okay. Okay. Notice that I can only add these if they're in component form like that. Otherwise, we got to do some other physics stuff. But in component form, we do that. Subtracting, again, I'm going to subtract the x's, subtract the y's, and to multiply by a constant, just like that scalar multiplication, I can multiply each of those values the same way. So I can add them, I can subtract them, I can multiply them. Okay. Now, I cannot multiply one vector by another at this point. We're not ready for that yet, but I can multiply the vectors by a constant. Okay. Again, that seems a little blurry, so you can't see that. So keep these in your bank. So as we scroll through, using these vectors, I want to find u is written as 3, -2. V is written as -1, 4. We're going to write a new vector, which is 3 times u minus 2 times v. Okay. So first I'm going to take 3 times this one. So 3 times 3 is going to be 9. 3 times -2 is going to be -4. And then 2. So 3u is going to be 9 -6. And then 2v is going to be, let's see, -2, 8. And I can write those out. We're going to scale each one of them. And so I've got 9 -6 and then -2, 8. If I subtract those, it's going to be 9 minus -2, which becomes +2, which is going to be 11. And then -6 minus 8, which is going to be -14. This is going to be my my W. Okay. The computation here is pretty basic. It's just adding, multiplying, dividing. So it's not going to be overly involved. Keep in mind that division is the same thing as multiplying by a fraction. So this right here, where you multiply by a scalar, you could multiply by a half, which would be the same thing as dividing by 2. So that property still works here, and that can be done. Okay. Okay. So again, we're going to leave the word problems alone. We're going to tackle those on Friday. On your homework, we're going to tackle. We're going to do numbers 1 through 22. We're going to do the odd there. I will post this assignment in just a second. Tackle these from page 551. Okay, you can get started on that and get that turned in tomorrow, and we'll be ready to go. Okay, thank you guys, and have a fantastic day.